Okay, in the last video, we had an introduction to molecular orbital theory. And now we're going to see how does molecular orbital theory apply to conjugated pi systems. Okay, so a review of some important things that we talked about in the last video. The number of orbitals is conserved. So if I start with 2 atomic orbitals, I get 2 new molecular orbitals. And for this slide, we're thinking about ethene. So we have and so each of these carbons is sp2 hybridized, and we have the overlap of an sp2 orbital on each carbon with one of the hydrogen atoms to form this sigma bond. And the third sp2 hybrid orbital on each of the carbon atoms overlaps to form a sigma bond between the 2 carbon atoms. And then the 2 remaining unhybridized p orbitals on each atom can overlap to form the pi bond. And so we have 1 p orbital on each of the carbon atoms, and so that's going to give us 2 molecular orbitals. We're going to get the bonding pi orbital and the anti-bonding pi orbital. The bonding orbital is lower in energy. Each of those carbons contributes 1 electron, and they both end up in the bonding molecular orbital. The other important thing, this is a fairly small molecule, but an important feature of molecular orbitals is that they're distributed over the entire molecule, right? They're delocalized, and that's going to be important when we go to our conjugated systems of bigger molecules. Okay, so now we're considering 1,3-butadiene. All 4 carbon atoms are sp2 hybridized, and so they all have an unhybridized p orbital that essentially they're bringing to the party. So I have 4 atomic p orbitals, and so I'm going to get 4 molecular orbitals. And the more nodes we have, the higher the energy is going to be. So the lowest energy way that I can combine these 4 p orbitals is to combine them so that they're all in phase. And so this gives me my lowest energy bonding molecular orbital. This is the only way that I can combine them so that they're all in phase. So if I combine them so that I get just 1 node, so I have these 2 are in phase, but then they're opposite with these 2, so I'm going to get a node in between. I get just 1 node, and so this is going to be my next highest energy orbital. When I then combine them so that I have 2 nodes, I get the next highest energy orbital. That we would probably describe this one as anti-bonding now, because now it's above the average energy of the 4 isolated p orbitals. And then the highest energy orbital I get is when I have 3 nodes, and each of the orbitals are out of phase with the one next to it. When we add our electrons, each carbon atom is contributing 1 p electron, and so my electrons fill the 2 lowest energy molecular orbitals. Okay, so let's consider a couple things that molecular orbital theory can help us explain about the properties of these conjugated pi systems. So we said before that the 4 pi electrons in butadiene will occupy the 2 lowest molecular orbitals. And so I've pictured those 2 here. So one of the things that we mentioned about 1,3-butadiene is that this sigma bond is shorter than we would generally expect. And we talked about the fact that these carbons are sp2 hybridized versus sp3 hybridized, and that was one potential explanation. Molecular orbital theory gives us an alternate explanation. So in this lowest molecular orbital, there is double bond character between carbons 2 and carbons 3, right? There's no double bond character in the second lowest molecular orbital, but because of this increased double bond character in the overall molecular orbital electron configuration, that contributes to the shortening of this bond, because we know that double bonds are shorter than single bonds. The extra stability of conjugated systems can also be explained by molecular orbital theory, and in molecular orbital theory, we note that the lowest molecular orbital that has 2 of the 4 pi electrons is delocalized over the whole molecule. And we know from our discussions of resonance that the more we can spread out electron distributions, the more stable it's going to be. So the fact that I can spread out these pi electrons through 4 carbon atoms is a particularly stable arrangement. And so this is why conjugated systems are so stable. Delocalization is fundamentally a stabilizing feature because I can spread those electron distributions out. All right, so here we see 1,3,5 hexatriene. This is also a conjugated pi system because there's only one single bond separating each of my double bonds, right? And now I have 6 carbon atoms that are going to be contributing to the conjugated system. So I have, each of them has 1 unhybridized p orbital, so I have 6 p orbitals. So I'm going to get 6 molecular orbitals. And again, the lowest molecular orbital is the one where I don't have any nodes. The next highest is where I have 1 node, then 2 nodes, then 3 nodes, then 4 nodes, then 5 nodes. I have 6 p electrons to put in, and so they go in the first 3 molecular orbitals. The last thing I wanted to mention about molecular orbital theory at this point is the concept of frontier orbitals. So the frontier orbitals are the ones that are most involved in chemical reactivity. And they are what are called the highest occupied molecular orbital, or the HOMO for short, and the lowest unoccupied molecular orbital, or the LUMO for short. And so just like with the valence electrons, these are the ones that are sort of the highest in energy in atoms. The frontier molecular orbitals are the ones when electrons are exchanged between molecules, which is what generally happens in chemical reactions. These are the orbitals that are most likely to be involved, and so these are often very important for understanding the reactivity of molecules. Another important feature of the HOMO and the LUMO, we've talked about the fact that electrons interact with electromagnetic radiation in different ways. For example, with IR radiation, this causes, when a molecule absorbs infrared radiation, it causes the vibrational energy of the molecule to increase. And depending on the types of bonds that are present in that molecule, different frequencies of infrared radiation can be absorbed. Well, the way molecules interact with visible and ultraviolet light is to cause electrons to jump from one molecular or atomic orbital into a new one. And so for molecules that are colored, that have color, very often what's happening when those molecules are interacting with visible light, we're causing an excitation of an electron from the highest occupied molecular orbital into the lowest unoccupied molecular orbital to give us a new excited state or an excited electron configuration following that absorption of light. So the frontier molecular orbitals can tell us a lot about chemical reactivity, and they also can potentially tell us quite a bit about the spectroscopic activity of those molecules.